behalf of Team Autobot, I'd like to thank you guys for all coming out this morning to hear all about our presentations, not only our project, but of course the rest of the team. Before we get too far in our presentation, we'd like to thank Dr. Luke for being our guide this semester, as well as General Interest for being our project sponsor, aka more that. My name is Ryan Gautier. I'm the team lead, and I work on communications and navigation.
I'm Ibrahim Abdelkader. I'm an electrical engineer, and I work on the vehicle design.
I'm Shane Gill. I'm a computer engineer. I work on the vehicle control and navigation.
I'm Omar Akers, software engineer. I'm the Scrum Master and the lead on the current team.
I'm Brandon Newgar. I'm an electrical engineer, and I work on navigation and parts of our robot.
And I'm Alex Anopoulos, and I'm a computer scientist, and I worked on data fusion and a lot of sensing equipment. So our project was based on NASA's UAS aerospace operations challenge, and what that did is it aimed at implementing UAVs in the national aerospace safely. That challenge has since been terminated, but we wanted to create a smaller scale model of that, which is ground-based, indoors, and controlled environment. And the project was meant to provide support for direct and autonomous control of the robot, sensing capabilities for the environment, and kind of a localization solution for navigation purposes. This is a high-level architecture of what our project looks like. There are 5 subsystems, one of them being a communication subsystem, which we'll talk about in a moment. But some key things to note on this. One is the robot processing subsystem. That's the center of our communications for this project. It's the center of our star network topology that we're using. All communication messages get routed through that. That and the robot control subsystem are both located on the robot in this project.
So as Alex referred to, there's nothing too special about the technologies we chose to use for our communications. We use the standard wireless network, as well as a wired USB connection on board the robot. What really defined our communication subsystem was the protocol we chose to use. As he mentioned, it's based on a star topology, so from sender to receiver, everything has to go through the RPS on the robot. And the protocol, we just transfer strings of data. For each string has a destination, a variable payload link, depending on what you're trying to do, and a tilde character to demarcate the end of the message.
This is a screenshot of our ground station. You may notice the Apple-like user interface. This is because we're using the Apple Corporate Framework to implement this with the Objective-C. Over here, we have the direct override tab that allows you to enter direct messages to control the robot directly. We have a couple of buttons to stop and to resume robot movements, and we have monitor mode that allows you to monitor the robot and whatever activity is going through. But before you can actually send messages, you will have to connect to the RPS first wireless. And the path support tab allows you to select a predefined path to send to the robot. As mentioned, we use the ground station to generate paths for the robot to travel using trig functions. So we enter the waypoints, and using these functions, we calculate the angle and the distance to those waypoints, and then transmit it wirelessly to the RCS via the RPS. This is a sample log data from the ground station. In the huge box, this is the ground station generating a path message. So it generates it, converts it, then sends it to the RPS, which drops it to the RCS link.
And here we can see a picture of our vehicle. It consists of 3 layers. Where in the bottom layer we mounted the control subsystem components that are on the remote machine. And then in the second layer we have our processing subsystem components. It has Raspberry Pi and 2 batteries. And then for our top layer we dedicated for our localization subsystem, where you can see the circuit is mounted. And then here we have a side view of our vehicle. And you can see at the front we use the 3D printed part to mount the electronic sensors that are in our fixed camera.
So, as Ibrahim just said, as part of our sensing equipment, we use a Pixie camera, and it can detect a uniform color object. It's 73 field of view, up to 30 inches away from the robot, and many times it detects objects even past 30 inches. So based on the size of the detected block and the relative position in the Pixie frame, we can detect the angle and the distance from the robot where that object is. What we do is we reduce the effect of ambient color from surroundings like Mazar shorts. We blur the image a little bit so it can't really detect anything other than that object, and it worked out really well. The distance error was never more than an inch, and the angle error was never more than 2 to 3 degrees.
And we've also included an emergency stop algorithm for our design, where we use ultrasonic range finders as a backup for our camera system in case the camera doesn't read
sort of kind of like a Loran type system. So we use 2 beacon pulses. Each beacon pulse goes into a set. As you can see here, we have 5 sets. And when we zoom in on these sets, we get our square waves, and we're using the leading edge square waves to find our TDOA. Unfortunately, however, we did have a big problem with our system. Our big system catches up. It catches a lot of your signals. For example, these evil little devices right here, that's what we turned off earlier. That's what happens when we turn on.
So as he said, we made the transition from TOA to TDOA back in late March, and after that transition, we were actually able to fairly quickly implement an algorithm based on a paper we found written by FIT online. We defined the parameters of our pulses in terms of the pulse duration as well as pulse separation, and we repeat this 3 times, and we average the results together to try to account for some of the errors that we can't really manually deduct from our calculations. We have some margins of error. We expect them to be pretty close to what, so the time that we measure for a pulse, potential pulse, has to be pretty close to the actual number for us to actually use that data. A big problem we ran into that we discovered late in the game, actually this maybe a week and a half ago, this is from a point that's equidistant from 2 beacons. So you would expect the voltages from the 2 beacons should be about the same. However, you're noticing that on the left, this is from a beacon that's been running for about a year, whereas that's a beacon we ran for just a couple weeks. So what we suspect is going on here is that between extensive usage and dropping of the towers, that these sensors just don't handle time too well. And as a result of that, what happened was that when you tried to test the algorithm, what would happen is one of 2 things. If you're on the blue side of the board, on the left-hand side, you always get the coordinates 8, 8. The reason for that is that you would never be able to receive tower 2s. But tower 4 could receive because that was the 3-week-old beacon. All other 3 beacons are a year old. On the right-hand side, you couldn't even resolve to a coordinate. The reason being is that the algorithm we use depends on beacons 1 or 3 always being in the pair that you're using. And because on the right-hand side of the board you can't receive those signals because of the sensor degradation, you can never resolve to a result. However, we did find one place on the board where all 4 beacons could be received, and that was in the exact center. We ran a series of 10 tests, and we got an average output for 8.8 was 8.105 tau and 8.059 tau, where we defined the unit tau to be a test area unit, equivalent to 3 inches. The standard deviation in both coordinates was less than or equal to about 0.5 tau, which is extremely good for our purposes. And these results kind of indicate if we had more time and or better sensors, we very likely could have gotten the accuracy that we need for the project. We were also able to get our target refresh rate at 1 hertz, which brings it about on par with what we would use if, say, we were using an outdoor DPS solution.
And regarding the budget of our project, last semester our cost totaled at around $450, where this semester we spent almost $710. That is because of some redesign decisions that we made at the beginning of this semester. And $500 for our total budget was allocated by almost Father as a sponsor for our team, and the rest was distributed amongst the team members. And you can see here that the project communication cost total was $583, and we have 126 ways to put the cost out because of some components that were broken and parts that were on the order.
Looking back on the project, there were a lot of things we would do better and a lot of things that we learned. We really wish that we would start on TDOA just a little sooner. As you can see from the test results that we showed, we probably would have been able to have a good implementation of it had we started quite a bit sooner. Unfortunately, a lot of problems came up with that time of arrival. In the first semester, we also
This is us sending the robot direct messages, forward commands, left, right, send it out of the text area and send it back to the beginning. This is the robot traveling a triangle path. It does this 3 times just to show you that it is traveling a triangle. Not really as accurate, but it's close.
Dead reckoning, no external source of location.
And here we're trying to demonstrate collision avoidance using e-stop, using the ultrasonic sensors. So whenever the robot detects an object like 7 inches to the sensors, it stops automatically. And once the object is clear, it keeps on moving. And this is us demonstrating that with a board. And now we're going to use a tennis ball to show that as well. As you can see, it stops, continues. When it gets the ball rolling, it does stop. Allow the ball to move faster than the ball keeps on going. And this is the same thing. And then and the next short clip will be demonstrating the pixie detecting an obstacle on the left-hand side, center, and on the right-hand side. This is data we get from the pixie showing us where exactly the robot is, how far it is, which direction, is on left, right, forward. That previous clip shows the robot stationary and the ball stationary. This one, the ball is moving while the robot is stationary, and we do get the same data as you can see. Whenever it detects the ball, it shows us where the ball is.
Moving away from us towards us.
And finally, in the last clip, the robot is going to be moving, and the ball will be moving as well. And we do get data for that also.
Any questions?
We have a few minutes for questions if there are.
No.
Okay, you say the worker is dead center. Are you saying if you moved it an inch to the left or an inch to the right, it didn't work? You gotta be
Get
kidding
one of
me.
those two results.
That's really tough to believe.
If you look here, we enforce a global threshold of 0.97 volts. So at least 1 of 3 consecutive readings has to be above 0.97 volts. And this is at 8 gauge. So if you move just over it, what happens is you have a period in that signal where it's going to be below 0.97, so it violates our rule. Maybe if we had more time, we could make it a little more resilient. It's a consequence of our implementation. We probably could have, with an inch, we probably could have still seen it. If you move several inches over, we aren't going to reject the signal completely because it's just too low. It's too close to our threshold of noise that we have already with the AP converter and the 0 state. So, yeah.
You had been able to get the localization working. How would you integrate that with the rest of your algorithm?
Well, based on, for instance, when we set it on a path, what we can do is, for every 2 localization hits, we can create a trajectory on which it's going, and each new localization update we get, we can keep updating where that's headed, and where it is on the board, and we can keep it on the path that we want to go, like the triangle path that Mark showed a bit earlier.
The question for Mark. You mentioned you used objective C. But just any comments on sort of message passing versus method calling as far as a way to go to an object-oriented design?
It's pretty much the same as Java. I mean, the reason why we chose to use Objective-C is because all our communication code was in C, so it's easier for us to embed it into our ground station code. So it just made life much easier for us. And in terms of message call, functions, it's pretty much as straightforward as any other programming language you use. If that answers the question.
It's just a different syntax. It's the same one.
So there are also a lot of available resources out there. Apple provides a good library for
you have a transition cost from one to the Java thing to the Objective-C thing? I find them very different.
We initially started getting Objective-C, so
I personally like Objective-C better than
I agree.
that's just personal preference.
They're both active brews, and we were using Mars computer as the ground station, so it was a little easier for them.
Any final question? All right. Well, thank you very much, Team Autobots.